Welcome to This Explainer. I'm your host, and, well, as a field ecologist, I essentially spend my days out in the wild studying what you might call the fundamental spending limits of life on Earth. Seriously, every single day, I'm out there looking at how the strict physical laws of the universe govern exactly how much life our planet can actually support. It's like this giant, fascinating puzzle to unravel. So, in This Explainer, we're going to trace the absolutely breathtaking journey of energy and nutrients. We'll follow it starting directly from the sun, flowing right through plants and animals, and ultimately arriving straight onto your dinner plate. Okay, let's dive into this. This fundamental question is practically my obsession. It's what drives all my research into primary production. I'm constantly trying to figure out exactly what controls the absolute boundaries of nature, and by extension, global food production. You see, every ecosystem on Earth is operating on a really strict budget. Just like you can't spend money you don't have in your bank account, an ecosystem simply cannot support life without the necessary energetic funds. So who actually holds the purse strings? Well, it all starts with the sun. But as we're going to see, having a massive incoming salary of sunlight doesn't automatically mean life gets to keep all of it. To really understand our planetary budget, we first need to define the metric that we ecologists use to measure the Earth's energy income. We call it primary production. Basically, this is just the amount of light energy that gets converted into chemical energy by autotrophs. You know, your plants, your algae, over a specific period of time. Now, get this. Every single day, Earth's atmosphere is bombarded by enough solar radiation to supply the total energy demands of the entire human population for 19 years. Crazy, right? But here is a truly surprising fact. Of all that visible light that actually strikes photosynthetic organisms, only about 1% is successfully captured and converted to chemical energy. Just 1%. And that tiny fraction sets the strict, non-negotiable spending limit for almost all life on the planet. And this brilliantly illustrates the hard line between the two foundational laws of ecosystems, the one-way flow of energy and the circular economy of chemical cycling. Think of energy as strictly a one-way street. Because of the laws of thermodynamics, every single time energy changes hands in nature, a huge chunk of it is permanently lost as heat. It flows through the ecosystem, and without a constant, fresh supply beaming down from the sun, most ecosystems would literally just vanish. On the flip side, we've got chemical cycling. This is the ultimate circular economy. Matter cannot be created or destroyed, so the exact same atoms of carbon, nitrogen, and phosphorus are endlessly recycled between living things, the soil, the water, and the air. It's a completely closed loop. To really grasp how that one-way flow of energy works for the plants capturing it, I like to think of it like a paycheck. Total photosynthesis is a plant's gross primary production, or GPP. That's the gross pay on your pay stub. But plants, just like us, have to stay alive, right? They have to burn some of those organic molecules as fuel for their own cellular respiration. You can think of those as the taxes they have to pay just to exist. What's left over after that is the net primary production, or NPP. That's the take-home pay. For us ecologists, NPP is absolutely the crucial number because it represents the entirely new biomass, the actual chemical energy that is now available in the ecosystem for all the consumers to eat. And yes, that absolutely includes humans. So, the crucial point is, once the plants have done all the hard work of creating that take-home pay, how efficiently is that energy actually passed up the food chain? Well, the answer is shockingly low. On average, a mere 10% of energy is successfully transferred from one trophic level to the next. That means an astounding 90% of the available energy is lost every single time something gets eaten in the wild. Let that sink in. This isn't just some minor inefficiency, this is a massive, fundamental bottleneck in nature that dictates exactly how ecosystems are structured from the ground up. Now, what's really interesting about this slide is exactly why so much energy is lost. Let's zoom in on a single caterpillar munching on a leaf that contains, say, 200 joules of energy, just to see where it all goes. Right off the bat, half of that energy, 100 joules, goes straight through the caterpillar and is lost as feces. It's not even assimilated into its body at all. Now, of the remaining 100 joules it actually absorbs, a whopping 67 joules are burned up in cellular respiration just to keep the little guy moving and alive, eventually dissipating into the surrounding environment as heat. So only 33 joules, just 16.5% of the original leaf energy, is actually converted into new caterpillar biomass. That tiny little slice of growth is literally the only energy available to the bird that eventually comes along and eats this caterpillar. And when you multiply that massive inefficiency across a whole ecosystem, you build a really rigid energy pyramid. If we start with 10,000 joules of primary producers at the base, the herbivores, the primary consumers, only get 1,000 joules. The carnivores that eat them, the secondary consumers, they only get 100 joules. I really want to emphasize this. This progressive 90% energy loss at each step severely limits the length of food chains. It sets a hard, undeniable cap on how many top predators an ecosystem can possibly support. It's the exact reason why a vast African savanna can support millions of grasses, thousands of grazing zebras, but only a very small handful of lions. The energy simply runs out. But hey, energy from the sun isn't the only thing controlling that base layer of the pyramid. Let's shift our focus for a second from energy flow over to chemical cycling. Because even with perfect, abundant sunlight, plants and algae simply cannot grow if they are missing key chemical building blocks. We call these limiting nutrients, and they act as absolute bottlenecks for primary production in the wild. The usual suspects? Well, nitrogen frequently limits growth in oceans and on land. Phosphorus is often the big limiting factor in freshwater lakes and older, highly weathered soils. And incredibly, in massive, crystal-clear ocean regions like the Sargasso Sea, primary production is actually limited by a lack of a micronutrient, iron. It literally has to blow in as dust from distant landmasses for anything to grow. Now, because these nutrients are limiting factors, what happens when we artificially add them to the environment can be incredibly dramatic. It triggers a cascading process called eutrophication, when excess nitrogen and phosphorus, often from human sewage or farm fertilizers, run off into coastal waters or lakes. They completely remove that natural bottleneck. And boom, this sparks a massive, explosive growth of phytoplankton. But those phytoplankton are short-lived. They soon die and sink to the bottom. Then, when bacteria and decomposers start breaking down that huge volume of dead organic matter, they consume almost all the available oxygen in the water. This rapid oxygen depletion creates these massive ecological dead zones where many aquatic organisms simply cannot survive. Let's move to and see how this builds into our understanding of human food systems and global food security. You see, wild ecosystems function entirely on the natural, slow recycling of elements, driven mostly by decomposers. Nutrients are carefully and meticulously cycled locally. Modern agriculture, however, it completely bypasses this slow recycling. To maximize our crop yields, which is essentially us trying to boost that net primary production to the absolute maximum, modern farming relies on continuous, massive external inputs of industrially synthesized limiting nutrients, like nitrogen and phosphorus. We have fundamentally altered global nutrient cycles just to keep our food supply growing at the same pace as our population. Which brings us directly to your dinner plate, and how human food security is inextricably tied to that 10% rule of the energy pyramid we discussed earlier. If a human eats a pound of soybeans directly, we are acting as primary consumers. We get that full pound of plant food and tap right into the most abundant base of the energy pyramid. But if we feed that exact same pound of soybeans to a cow and then we eat the beef, we're acting as secondary consumers. Because of the enormous energy lost to the cow's own cellular respiration, its movement, and its waste, that 1 pound of soy yields only about 1/5 of a pound of beef, sometimes even less. Eating meat is, thermodynamically speaking, an incredibly inefficient way to tap into the sun's energy. The ecological laws we've explored today aren't just abstract theories drawn up in some ivory tower lab. They are the literal operating instructions for our survival on this planet. And the science is incredibly clear here. Agriculture worldwide could feed many more people and require far less land if we just fed more efficiently. By acting as primary consumers and eating plant material directly, humanity can effectively hack the energy pyramid. We completely bypass that 90% energy loss at the secondary level, allowing us to capture a much, much larger slice of the ecosystem's energy budget before it's inevitably lost as heat. It's a huge game changer. So, we arrive at the ultimate question of this explainer. Nature operates on a very strict ledger, permanently bounded by the physical laws of thermodynamics and chemical cycling. Earth's energy budget is absolutely capped by the exact amount of solar radiation plants can turn into organic matter. Knowing that every single step up the food chain wastes 90% of that precious energy, will we choose to align our agricultural and dietary systems with these ecological laws? Will we eat efficiently enough to feed the world? I'll leave you to rethink the thermodynamic footprint of your very next meal. Thanks for joining me on this explainer.